Hello and welcome to the video on principles of carburation. We're going to start by talking about the purpose of carburation. And the purpose of carburation we see is to provide the combustible mixture of fuel and air necessary for the operation of the engine. Let's take a look about that for a little bit. The fact that it's a combustible mixture tells me that it's got to be a mixture of a certain proportion. We've talked about that, how there has to be a fuel-air ratio of fuel and air to burn. And it's for the operation of the engine. We're talking about aircraft carburetors here, but this would apply also to cars. You know, the engine operates under changing conditions of temperature, pressure, altitude, etc. And so that means that the mixture is obviously going to have to change. One of the things before we get started a little bit is to think about the fact that we're speaking of fluids. And normally, we think about fluids as just liquids, but truly fluids are liquids as well as gases. And within the realm of what we're talking about here, fluids that are liquids, pretty much their volume is constant and their density is constant. Yes, I know that under different conditions, the volume, they expand and contract as they heat and cool, but for what we're talking about, we're going to call that negligible. It doesn't matter. Gases, however, their volume very easily goes up and down, and then their density also goes up and down. So we have to keep those things in mind. We're going to look at something that's going to come back to us, and that's atmospheric pressure, and explaining what do we mean by atmospheric pressure. So if I have a container, and it's full of mercury, like this, and it's open on top, and I put in a tube that has a vacuum at the top, and press it down into the container. The pressure of the atmosphere, if this is a vacuum, will cause the mercury to rise to a certain amount. If we put a ruler next to it, if this is 29.92 inches, we could say that the atmospheric pressure equals 29.92 inches of mercury. Mercury the symbol is Hg. So you get that idea that the atmosphere presses down on everything around us, and we measure it for some reason in inches of mercury, and it's just the amount the atmosphere would press mercury up a tube with a vacuum. If the pressure gets higher, it could be 31, 32, etc. If the pressure gets lower, it could be 27, 28, etc. So we can measure it in inches of mercury. One thing to think about with airplanes and airplane carburetors, if I take this very same bucket of mercury and tube, and I've got it here on Earth, if I go up in the atmosphere to this location, I go up in altitude, the pressure will decrease simply because there is less atmosphere pressing down here than there was here. Again, just some oversimplified little principles about atmospheric pressure to keep in mind. Look at another thing real quickly to get an idea of, and this is the pressure differential. If I have a U-shaped tube and the pressure on both sides is 26 inches of mercury, the fluid in the tube will go to the same level. I take the same tube, if I increase the pressure here to 28 inches of mercury, keep this one still at 26. Notice the fluid rises a little bit because of the increase in pressure here. Let's talk about Venturi tubes briefly. A Venturi is basically just a tube with a reduction and then an expansion of width. It's kind of a magical tube because of what happens. One thing to keep in mind is that with this tube, the same quantity that entered exits. So that being said, I've got a certain amount of air here, and then the same amount, and then this certain amount here, the same amount, and the same amount. This is called the throat of the Venturi, and in order for this to be the same amount of air here, the velocity has to increase. And if the velocity increases, the pressure decreases. And this is based on something called Bernoulli's principle. You've heard about this before in studying aerodynamics. And the basics of the Bernoulli's principle states that the total energy of a particle in motion is constant at all points on its path. So these little molecules of air here have a certain amount of energy. And of the energy, some is velocity, some is pressure. These molecules of air in the throat have the same amount of energy. However, the velocity has increased, so the pressure must have decreased because it's the same energy. So how do we use this? How do we use the unequal pressure in the tube and the Venturi tube? So here I have my Venturi, and if I have X psi here, and if the throat diameter is 1/2 the diameter of the tube, the pressure here will be half of X, and then the pressure here is back to X. We've talked about that in the last slide, so this is what's going to happen. So let's take a little float chamber and let's fill it with gasoline. The gasoline is in red, and we have atmospheric pressure pushing down right here. And it comes over to a tube, and the tube is placed in a Venturi. And you see the air moving up in the Venturi, which causes the pressure here to decrease. The pressure at this point, the pressure here in the throat is less than, I'll call that pressure throat, is less than the pressure of the atmosphere. There's less pressure pushing down. So just like we had the tubes where the fluid rose, here the fluid, the gasoline, rises and goes out into the airstream. It's just as simple as that. More pressure here, less pressure here, the fluid has to go up. One thing to note that's very important, and we'll talk about this more later, is this is called a discharge nozzle right here. And note that the height of the discharge nozzle must be greater than the height of the gasoline in the float chamber. The reason for that is if this gasoline here was higher than this gasoline, when the engine was stopped, the gas would all run out and leak out. So that is it for the basics of carburetor principles. I hope this helped give you some basic knowledge to go with, to study more and learn. So thanks for tuning in.